Why is three diagonal not diagonal?
Hmm? Well, when you consider so-called Gram-Schmidt orthogonalization, it's possible to present Hamiltonian in three-diagonal form. It is triangle. No. It's possible to represent it just in this way.
Could represent it as think of that.
No, well.
Because at least if H, I believe if H is Hermitian, right? Self-adjoint, that L is also operator Y is also self-adjoint. I mean, as a superoperator, right? Then I think there is some use in this representation.
Exactly.
Diagonal, because we can apply this.
Exactly. Yes, and for instance, when you consider generic Hermitian matrix, it can be presented in three-diagonal form.
Which way?
No, it depends on the operator. So okay, so we start with some operator O, and of course, this matrix depends on operator O. Yeah. Well, it is to some extent presented its definition of the basis K. And then we can evaluate this Lankash coefficient step by step. There is the current procedure starting from 0, A0. We can write down step by step and get this three-diagonal form of the Liouvillean. Okay, so when we consider eigenvalues of this Lankash matrix, we get actually the consider eigenvalue problem. We get the Hopin problem in this case, and the function Phi correspond to peculiar overlap of these operators, and it can be shown that this Hopin problem is nothing but the open to the chain. So the coefficient an and bn have the following form that, in some sense, in quite direct sense, we get the representation of the open to the chain. And another representation is the in terms of DSYK passes, and in what follows, I'll use so-called Krylov complexity defined in this way, and the behavior of Krylov complexity at large T generalizes the Lyapunov exponent for the classical Gauss. So it's interesting to investigate this object. Okay, so it has been shown that when you consider the behavior of Lankash coefficients at large n, it actually related to the behavior of Krylov complexity. And here is some cartoon picture how we start with some simple object and then consider the operator Gauss problem. So we start with one operator and then we get the operator Gauss problem. And equivalently, we consider the hopping on the Toda chain. There are different ways to handle with this. Yeah. Okay, it's a level of the Krylov basis, and to some extent, well, you could think it as the some partial way of time evolution. So it's related to when Liouvillean x to the nth power. And then we get some level of the Krylov chain, and this is just n here. So approximately. So it's not exactly the time, but It's a power series. If we multiply it by t to the nth power, we get a kind of time dependence. And remarkable result of that paper is that we could distinguish a different behavior just looking at the behavior of Lanka's coefficient. So when we consider linear behavior, we have chaotic behavior, square root corresponds to integrable model, and when its Lanka's coefficients are constant, it corresponds to 3, 1. So, and now we would like to apply the Krylov basis to evaluation of autocorrelators. So we consider a correlator at time 0 and operator at 0 and its correlation function with the same operator at time t. So we have in terms of Krylov chain, we have just a random walk on the Krylov chain. And first of all, I would like to present some analytic results concerning this autocorrelator, which explain how the KPZ scaling emerges in this language. First, I would like to mention, then we'll consider its important result by Dimitrov and Edelman, who considers the so-called beta ensemble in the matrices with different values of beta. And they have shown that for the Gaussian measure of matrices, any Hermitian metric can be presented in 3 diagonal form. But there is some price. So we start with the random matrix. What is the price for randomness? It turns out that in this 3 diagonal representation, the different matrix elements in this way are distributed with different probabilities. So this is the way for the randomness of the initial matrix.
Tell me if I'm wrong. So we can come up with a particular representation of any finite dimensional Hermitian matrix, which then gives maybe not Gaussian, not normal, not simple, but some well-defined distributions of the coefficient that can be then interpreted in terms of like random hopping on a chain or something like that, right? With nearest neighbor.
Exactly. Exactly. And for any potential here, we consider these results concern the Gaussian model. If you consider generic potential for this distribution, it has been shown more recently that the same is true. But formulas are more complicated. Instead of this simple probabilities, there are probabilities which depend on the potential. Yeah. Okay, so when we consider the finite number degrees of freedom, so we consider the situation when Krylov chain, when we have system with finite number degrees of freedom, it can be shown that the whole Krylov chain is finite dimensional. So there is finite number of sides in the Krylov chain. And then the whole number is proportional to the, well, here is denoted as e to the power 2s, but it turns out that there are several behaviors, intermediate behaviors of the Lanka's coefficient, which correspond to different time scales. And what is important, there is the Gauss situation. So the whole behavior of Lanka's coefficient correspond to some linear path dependence, some kind of plateau, and also descent path. So the whole graph of the Lanka's coefficient Bn involves 3 different domains: growth, plateau, and descent path. And it will be important in our story. The restriction for the size of the spin chain looks as follows. So it's a kind of not complicated mathematics, showing that the dimension of the Krylov space cannot exceed this value. And now we would like to evaluate the autocorrelators in the Krylov space, just the return probabilities for on the Krylov chain, and it depends on time. So when we consider autocorrelators, we have some time, and the question is what time we would like to select. And we would like to select the time proportional to the length of the chain. And actually, in the numerical experiments 5 years ago, that people consider approximately this value. So what happens in this situation? When we consider the length of the time is proportional to the length of the chain, we could use some mathematical results. And in 90s, there is a very well-known claim that the random matrix near the spectral edge behaves as differential operator. And the point is that more exact result, it turns out that there is additional term. And so when you consider matrix, three diagonal matrix, at the spectral edge, it reduces to the random differential operator, not the regular deterministic operator, but to the random operator. And there is the mathematical theorem, so this very exact result, that when you consider that the spectrum of this operator near the power of this three-diagonal matrix is related to spectrum at the spectrum level. So we have spectrum of two objects, and here is stochastic area operator. This is this guy. So we have area operator with stochastic term, and it turns out that there are mathematical strict mathematical result that relate the late time, so that is large T behavior of the powers of matrices with stochastic area operator. It is exact result. And just this result provides us the answer where this with where this KPZ scaling KPZ scaling comes. Look at this equation. So we consider this is return probability on the Krylov chain. This is nothing but autocorrelator. On the other hand, exact result that this is solution to KPZ equation when we consider LHK, which correspond to LHT in this language. That is why when we turn to the Krylov basis, we have three diagonal matrices. We consider late time, that is large power of this three diagonal matrix. We could use this mathematical result to show that indeed we have a KPZ behavior for autocorrelators at late time. So this is analytical result, but it is available only for the Gaussian case. This is quite complicated analysis by mathematicians, but it has been done. Okay. 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 So we consider stochastic area operator, and the claim is that the power of three diagonal matrices in this way spectrum of this of the left-hand side coincide with the spectrum of this operator. This is the key relation. So this is exact result. Here is we still have no KPZ, just relation between spectrum of three diagonal matrices and stochastic area. And well, M, okay, M is the let me previous. M is three-diagonal matrix in the Krylov basis. We start, we consider the Krylov basis. We have three-diagonal matrices. When we consider evolution in three-diagonal, in the Lancash, in the Krylov space, we consider the powers of this stuff. Then we use, this is the left-hand side. So we consider the representation in terms of three-diagonal matrix in Krylov basis. This is the theorem that the behavior of this stuff, which provide you the autocorrelators, is related to behavior of stochastic area operator. Stochastic area operator looks as follows, and finally, when you consider, so we have a set of relations. As the next point, we use the relation between powers of matrix and spectrum of operator. Then we use the behavior, the spectrum of operator is related to the partition function of this polymer. So this set of relations provide you the interpretation of autocorrelators, which are right-hand side, and the solution to KPZ equation. But let me mention once again that analytically we could provide this relation only for Gaussian case. For Gaussian case correspond to area operator, and there is no analytic result for arbitrary potential. However, now we could use the numerical tools and analyze what happens at numerical level. And there are, so I have mentioned that there are three domains in the Lancash coefficients. When we have growing Lancash coefficient, it can be shown and cut off by hands there at some level. It turns out that we derive the KPZ scaling for corresponding autocorrelators in all cases, both for random and for deterministic. And okay, so when we consider descending part of trajectory, it can be shown that once again we have transitioned to KPZ scaling, but in this case we have no a kind of phase transition, but it's a kind of crossover. And now we should glue all this all parts of the Lancash dependence. And okay, here it's the growing part. Okay, so let me summarize this part of my talk. There is a transition from the usual Gaussian behavior of fluctuation to KPZ behavior of fluctuation at Heisenberg time for autocorrelators. That is, when we consider the autocorrelators for generic operators in the Krylov basis at very peculiar times, then we get the KPZ behavior of fluctuation. It is crossover, so it's not a kind of phase transition, but it is crossover, and this is our result is possible explanation for experimental data. And let me emphasize that it's not useful for Gauss diagnostics. So initially, the people suggest that this behavior could be used to recognize Gauss, but it turns out that such KPZ scaling emerges both for chaotic and for integrable cases. So this is a summary of the first part of my talk. Well, numerical experiment. I mean the first paper by Prosen et al. 5 years ago, who investigated the numerically for finite number of spins, the autocorrelators at a late time. Yeah, in spin chain. Yeah, and moreover, there are some experimental, real experiments. Not numerical, where this KPZ scaling indeed has been observed for late time. So it is possible explanation. So this is very general behavior, and it can be explained in behavior in terms of Krylov chain for operators. So of course, here we consider only operator autocorrelators. For instance, when we consider the complicated correlator of different operators, where we have a Krylov chain for each operator, and there is still open question how they teach each other. So it's open question how to evaluate generic correlator in the Krylov basis. It's a good question, but it's still unknown. But for autocorrelators, we get very precise answer. Yeah. Yeah. Okay. So yeah. It's the next point of my talk. Yeah. Okay. So let me turn to generalization of this logic to SYK, and more it's most suitable to consider double-scaled SYK, because in that case the Lancash coefficients are known. They are expressed in terms of overlaps of Q Hermits. And this is work in progress. So Lancash coefficients looks as follows. So very simple, and we could just work with this behavior of Lancash coefficient, and we would like to investigate the fluctuation of Krylov complexity. So in the previous example, our finding can be reformulated as a peculiar fluctuation of Krylov complexity. Not Krylov complexity itself, but fluctuations. And now the question is, what could be said about this object? Here is definition of the object we would like to discuss. Just it's clear what is going on, and it turns out that we have a transition from the convenient Gaussian behavior and so-called ballistic behavior. Instead of 2/3, here we have additional critical exponent, which is 1 here. And so at large Q, sorry, at small enough Q, we have the ballistic behavior. What could be these results used to? So let me know that generically, when we consider diffusion problems, we have 3 different regimes. So we have, it's possible to have so-called subdiffusions, usual diffusion, which correspond to critical exponent 1/2. It's the Gauss Brownian motion. Subdiffusion when it's less than 1/2. And superdiffusion large than 1/2. And KPZ scaling in the same language correspond to subdiffusion, and this behavior in double scale SYK correspond to superdiffusion. And what we have found is that we have indeed superdiffusion behavior. And let me note what could we extract some interesting information about something else from this superdiffusion behavior. Let me note that double scale SYK are presumably related, quite precisely related to sign dilaton JT gravity, and it's related in a less strict way to three-dimensional de Sitter geometry. And the corresponding is interesting. So Krylov complexity corresponds to length of geodesics in the gravity side. Therefore, when you consider the fluctuation of Krylov complexity in double scale SYK, it corresponds to the fluctuation of lengths of geodesics in the double scale SYK. And we could, in gravity, sorry. And therefore, we would like to, it's possible to look at diffusion at gravity side from the diffusion of the Krylov complexity in double scale SYK. And remarkably, it turns out that indeed the superdiffusion, just the same coefficient 1, has been found argued, not a theorem, but there are several arguments that indeed we have superdiffusion in de Sitter. It matches the superdiffusion in double scale SYK. So this is some use of fluctuation behavior in the spin chain on the boundary in holographic sense with the fluctuation of some object here, the length of geodesics in the bulk, gravity bulk.
Your proposal is central. Right?
No. It's result. It's proposal by Susskind and Verlinde. Now our result is no. This is known.
Gravity and right?
Yeah.
What this was proposed by the what is the central about the complexity who proposed them, and in which versions of?
Oh, in both of them actually, there are some papers. Barbon, Binovich, and some else, and Verlin. There was a paper of Verlinde. Just about Krylov complexity. Okay. It's Barbon, Rabinovich, and some else. It's about 2 years ago, something like this. Yeah, this one, yeah. Yeah. The second is some version of ADSFT by Susskind and Verlinde, and there are some argument that is true as well, but I do not. Okay, so this corresponds to Susskind and Verlinde. Presumably for both. So there is no, actually it works for both. But of course, it's not a theory, but there are several arguments. And indeed, for sign dilaton, it's exact relation. And here, with some, yeah. both. And we have compared for de Sitter, and there is superdiffusion in de Sitter, indeed, and indeed we have superdiffusion for Krylov complexity. So, to my mind, it's nice to have such additional arguments in favor of this line. Okay, so let me now turn to the second point of my talk. It's our paper with several co-authors, and now the question is, we consider quite a generic system, and we will discuss once again the matrix Hamiltonian. So we consider some matrix Hamiltonians and evaluate the so-called quantum matrix, and it's well known that the quantum tensor has the quantum matrix as symmetric part, and the Berry curvature as antisymmetric part of the tensor. So we have both of them, and actually we focused on the real part of this situation, and it was suggested about 10 years ago that if you consider the quantum matrix, it could be singular. It's the mark of singularity. That is, we have some criticality. We have singularity in quantum matrix. On the other hand, it also marked the integrable points. So to some extent, integrable points in the family of perturbation looks as a kind of attractors. So to recognize these pictures, it's necessary, it's possible to investigate geodesics on this way. And so we consider quite as simple as possible situation, but for two-dimensional parameter space. So we consider random matrices, and we add two additional perturbation with Hermitian matrices parameterized by two parameters here, and all of them have Hermitian Gaussian probability, and the matrix has been evaluated the second derivative with respect to x y at origin, at point. There is no the way to recognize geometry of the space. And the second way, second model we have discussed is we start with integrable model. We mimic the integrability. We have diagonal matrix and have no correlation between eigenvalues. Poisson distribution, and according to Berry-Tabor conjecture, it corresponds to integrable system. And what we have found, so it turns out that for there are two findings. First of all, we found that we have for a chaotic point, the induced geometry of the parameter space is smooth. So we have here in the parameter space half sphere actually, and on the other hand, we have when we consider integrable point, integrable model, the geometry in agreement with expectation, quite general expectation, have a kind of singularity. It is conical defect. So we get a conical defect in the space of parameters. And for n equals 2, when we consider 2 over 2 matrices, it can be done by hand and it can be evaluated. This is precise expression for the matrices. This corresponds to conical defect. But when we consider the consider large n situation, we haven't succeeded in writing down the explicit analytic expression for the matrix, but instead we turn to the numerical simulation of the big clusters, and indeed we have found interesting situation. So for we get the intermediate. So the question is, if there are some integrable regime, chaotic regime is something in between. And indeed, numerical simulation up to 6,000 for the size of the matrix, big sizes of the matrices, we could get indeed 3 different behaviors. So remarkably, we have reproduced the existence of extended non-ergodic matrices phase in the version of, this is the version of so-called Rosenzweig-Porter model. And indeed, we get previously there are marks of this intermediate regime just from consideration of the model. And here we have shown that the same 3-phase structure can be deduced from the quantum matrix. So we consider the perturbations of the model, and indeed we could recognize all these phases. That is the quantum matrix is quite useful for identification of different phases. So this is okay. And what is the mark of the intermediate phase? It is the fractal dimension between 0 and 1. So when you consider fractal dimension equals to 1, it's chaotic. Equals 0 is integrable model, and when you consider intermediate fractal dimension, it's intermediate situation, and indeed we have such behavior.
Like power behavior, or in terms of the calculated fractal dimension?
Power behavior. So power behavior of the we consider wave function psi squared times to the no, it's just power of the wave function. It's possible to do it numerically for this matrices. Just consider eigenfunction, evaluate these moments, and extract this value. Indeed, it turns out that intermediate regime we have a fractal dimension situation. Okay, so there is some. Okay, so there is. Let me skip this slide. There is some surprise. It turns out that, moreover, we could get it's quite non-trivial results that we get also the Berry curvature. So the Berry curvature, it looks like usually when we consider the Berry curvature, it looks like the field of the monopole or some vortex or something like this. And here we get situation when the source of Berry curvature is a kind of string. So there are a few examples of this nature in the solid state physics, so-called Berry ring, and a bit surprisingly, we get the Berry ring in this situation as well. Okay, so let me turn to conclusion. First of all, we have explanation of present possible explanation of KPZ scaling for autocorrelators in the spin chain, and it seems that it's quite generic situation for finite systems. So when we consider finite dimensional Hilbert spaces is the same, we get for double scale SYK, we obtained transition between KPZ scaling and ballistic. It provides some additional argument in favor of double scale SYK de Sitter. And we get indeed get the singularity between integral points of parameter space as expected from quite general grounds, but still there is no theorem. To some extent, it is new, but quite generic example of the nature. And also there is non-ergodic. We have identified all phases which are present in two-parameter situation, and that is why this object is good for identification of phases. And of course, there are a lot of open questions. So we considered only two-parameter space. When we consider, for instance, three-parameter space, there could be more complicated geometry, maybe more complicated regularity. So it's interesting question to investigate the Anderson localization and PPZ in gravity, in the Krylov picture. To some extent, it's open question. Moreover, there are interesting questions concerning the well, when we consider the double scale SYK, so-called chord basis is used. So we consider circle, we have a set of chords, and these chords provide you the Krylov basis. On the other hand, this chords picture is closely related to knot invariance, and on the other hand, we know that three-dimensional de Sitter space is described by the Chern-Simon theory. Therefore, the picture of Wilson line in Chern-Simon theory is very suitable for the chord picture. So it seems that the double scale duality between double scale SYK and three-dimensional de Sitter can be also linked using the knot invariance. Okay, so okay, thank you for attention.
Perhaps, again, thank you for brilliant, many impressive things. I just have one question. You have dwelled on different phases of quantum chaos, and I wonder what can be said about the interplay of these three phases that you've shown us and say classical version.
Okay. Yeah, okay. So it's a good question. So when the question is whether these three phases, how could be recognized in the classical limit. So
say Anderson localization disappears.
Yeah.
By interference, right?
Sure. Okay. Nevertheless, we know that in the classical dynamics there are so-called KAM. So when we have system with n degrees of freedom, then when we have single degree of freedom, just Hamiltonian is chaotic system. When we have n integrals of system, then we have usually integrable situation. In between, when half of the Liouville tori has been destroyed, we have K and M. And generically, it's once again, it's not theorem, and there are investigation concerning this point, whether this non-ergodic extended phase with fractional dimension exactly correspond KAM in the classical limit. It's an open question, and there are some papers on this point, but general expectation is that it's indeed the case, that this intermediate situation corresponds to partially destroyed Liouville tori. And also, okay, and also there this can be related also to the presence of separatrices. So another way to handle this question is to relate it with the presence of separatrices. But the question is correct and important and partially open. There is no complete understanding of this intermediate phase at the classical level.
From the top, so there you have the plot, which clearly distinguishes between free theories, integral theories, and chaotic theories. Right? So how do you get it? So we just considering several examples by doing numerical separation.
Which one? You mean this one? What do you mean? Okay. This one. Well, it results from the paper of Parker, of Doshkin, Alton. This is the famous paper where the use of Krylov basis has been introduced. So before that paper, nobody was interested in this Krylov basis, but it turns out that it works well. And they have shown that when we have behavior of Lankash coefficient on the set of examples, it's once again, it's not theorem. No, there are no theorem in the still on this point, but in many examples they have such behavior. And now it's believed that it's true. Okay, so I guess it's observation, not theorem, a lot of examples which confirms this behavior. All of those, so we now consider different chaotic systems and evaluate the Lankash asymptotic of Lankash coefficient, and when you get linear behavior, yeah, it corresponds to chaotic. Square root behavior is integrable. And it has been shown that the behavior of Lankash coefficient can be traced into the behavior of spectral four factors. It's another way to recognize a different system in terms of spectral four factors. And it can be shown that the behavior of Lankash coefficient can be mapped to the behavior of spectral four factors. Yeah. Yeah, true. Yeah, it's asymptotic. So it's asymptotic behavior at very large n. So in intermediate situation, we could have different function. And indeed, for different model, we have different behavior of bn's, but for integer situation, the same asymptotics. Yeah, well, I see your point. Yeah. Okay, it's a kind of degenerate situation of the stuff, yeah, exactly. Well, it's defined for operator is defined uniquely at the point, but it depends strongly on the operator. Yeah. Well, if you select operator, you find out the Lankash coefficient uniquely, step by step. So this is a recursion procedure. And that's all.
What prevents you from writing Hamiltonian with any determinants beyond math?
Well, it's possible to consider a generic, and for instance, when in our pictures, we consider okay. Here are some alpha here are just different powers. So we investigate what is the dependence on the Planck coefficient b to the n to the power alpha here. So with three different coefficients, you see that, of course, there are some differences, but the asymptotic for the late time asymptotic is here. They have the same asymptotic behavior. For what is important, indeed important, when you consider the difference between infinite dimensional Krylov chain and finite dimensional. When you consider infinite dimensional situation, we have only growth part of the coefficient, but for finite, we have both of them. Yeah. Yeah. Indeed, I'm not expert in this stuff, but as far as I know, they have in mind the problem of thermalization of the different, some relation with at least the quantum computers. The name of quantum computers are present in their papers, but I'm not an expert at this point at all. Maybe these are just the words.